Well, good afternoon. This is a model test recording, and today we'll be looking at the difference between star delta and delta star transformations. So, well, not the difference really, but how to get the equation of a star delta transformation. So, in case you don't know what a star connection is, I'm going to draw it for you right now. So, I'll write the word star. Let me get a brighter yellow. Oh, that's how that works. Okay. Yes, so star and delta connections. So I'm gonna write star here, a star connection, and this is what it looks like. So I'm gonna draw it for you. So you're gonna have a resistor here, and then you're gonna have it branching off into two parallel resistors basically. But it's 3 resistors in total. And this, my friend, is the star connection. Now I'll call this Z1, Z2, and Z3. And what I'm going to do now is say, well, this is the star connection. Well, what's the delta connection? Oh, by the way, this is obviously point 1, point 2, and point number 3. Now the delta connection is similar in that there's a point 1, there's a point 2, and there's a point 3. But the way it's connected is different. The resistors. So we have this, and a resistor between the 3 points. And this is point 1, point 2, and this is point 3. Now I'm telling you all of this because there's an equation on how you can convert a star to a delta. So let me go on a new layer and use a different color. So this is the star transformation, and there's an equation that says, well, if you've got this given star transformation and you want to say get the equivalent resistance of the between the nodes point 1 and 3, for example, right? That's the equivalent resistance. That's what's over here. Oh, speaking of which, I gotta get the color for this, the name for this. So we'll name this ZB, ZA, ZB, and ZC. All right. So how do you convert from star to delta is what a lot of people ask. So here's how you're going to go about doing it. So they give us an equation that says, for example, ZA, which is the resistance, the equivalent resistance between point 1 and 3. So ZA is equal to, and this is the equation, Z1, the product of the sums of the individuals in the star. So Z1, Z2 plus Z1, Z3 plus Z2, Z3. All divided by the one that's not adjacent to the 2. So since we're trying to connect between point 1 and 3, the adjacent one is point 2. So Z2. And this is the equation that will give us the equivalent resistor of the equivalent resistance of ZA. Now there's an inherent problem with this. Well, there's no inherent problem, my bad. It's just that hold on for a second. There we go. Oh, I see, that's how it works. Alright, so given that this is this equation, my goal to you today is to derive this equation or to explain how it even occurs. How did we logically come to this equation? So to begin, what I'm going to do is I'm going to say, well, our goal is to get the equivalent resistance from between points 1 and 3. So resistance at the end of the day is this resistance. Let me write it in a bright reddish color. Let's go with bright blue. Resistance is the amount of voltage it takes to let 1 ampere of current to pass through a circuit. So in this scenario, we want 1 ampere of current. We're going to imagine that there's 1 ampere current flowing through here, and then we're going to try to get the resistance. Well, if 1 ampere is flowing through here, what we end up getting is Z1 plus Z2. That makes sense, right? You know, if 1 ampere is flowing through Z1 resistance, then the equivalent resistance is Z1 ohms. So RT is equal to Z1 plus Z2. Z3, my bad. Z1 plus Z3. But here's the thing: Z3 will have a voltage of Z3 because it's 1 ampere flowing, so the voltage is Z3, and that Z3 voltage will also be dropped. That voltage will also be dropped across this resistor. It'll be Z3 volts will be dropped across this resistor, and if Z3 volts are being dropped across this resistor across Z2, then we have a current, and the current, you can call this bypass current or whatever. This is a separate current. The current would be equal to Z3 volts divided by Z2 ohms. So we have an extra current. I'm going to use this purple now and say, okay, so there's this extra current. Let me write that again. There's this extra current coming in here, and it has to come from somewhere, so it's obviously going to come from here. So the current here is Z3 upon Z2, and it goes across from this. It has to come from somewhere, so it comes from the base here. And we're going to make the assumption that both of these are grounded to better illustrate the point. And so if we make that assumption, what we end up seeing is that we have Z3 upon Z2 amps coming through this resistor Z1. So Z3 upon Z2 amps. How do we calculate voltage? The voltage dropped by this Z3 upon Z2 amps. Well, voltage is equal to current by resistance. So the resistor is Z1. I'm trying to get the voltage drop of Z1 because of this little extra current thing. So what ends up happening, we end up getting Z1, which is the resistance, and the current through it, which is Z3 upon Z2. And so the final equation becomes RT is equal to Z1 plus Z3 plus the value that we got here for the equivalent, plus the voltage dropped to the other 1 ampere flow over here, which is this equation over here. So we know the voltage dropped across here is this Z1. So, well, the total resistance for 1 ampere to flow over 1, and this is over 1 as well. So we end up having Z3 upon Z2 times Z1. And if we were to pull all of this together now, so what we're going to multiply all the numerators by Z2, and we're going to divide by Z2. So it's going to work out the same, but watch this. So the final equation then becomes Z1, oops, let me get a brighter color for that. Z1 Z2 plus Z3 Z2 plus, well, the Z2 and the Z2 are going to cancel out each other, so we just get Z3 Z1 all upon Z2, which is the same, let me highlight this, which is the same as the initial equation we got here. So I hope this was insightful in some way in explaining how is it we do star to delta transformations. Thank you.